Okay, so this is the video for Limits Day 3 notes. We're continuing our discussion on limits, and we're going to talk about the idea of continuity. Whoops. And so continuity stems from the word continuous. So we're saying if a function is continuous at x equals c, if all of the following are satisfied. So first of all, that point has to be there. F of c has to be defined. Also, the limit has to exist. And the last one kind of combines those two. That point has to be the actual limit. Okay, so these are all not continuous. We can see this at C. There's a kind of a slight difference in each picture. So looking at A, we can see that as x approaches C, we're getting closer and closer to the same y value, but there is no f of C. All right, so the limit exists, but f of c is undefined. All right, and so this kind of falls under the number 1. All right, I'll put that down here, number 1. All right, and so let's look at B. Here we can see that f of c is defined. It's up here, but as I approach c from the left and from the right, that it's two different numbers, so this limit does not exist. The limit as x approaches c does not exist because it's two different numbers from the two different directions. Okay, and so that's like number 2. This limit does not exist. All right, here we've kind of got both situations going on. We have f of c existing, we have the limit existing, but the limit as x approaches c does not exist, does not equal f of c, and that's number 3. Okay, so if any one of these things is happening, we're not continuous. And we can see obviously from the graph why we're not continuous. Algebraically, though, this is why. Okay, so let's look at this idea of a one-sided limit. We've kind of already been talking about this. The limit of f of x as x approaches c is L, if and only if, that's what that means. The limit from the left as x approaches c from the left, put yourself a little note here, of f of x equals L, and the limit as x approaches c in the little plus means from the right. Okay, it has to be the same. All right, that's the only way you can have a true limit. So for the graph above, the limit as x approaches c from the left and x approaches c from the right have different values. Therefore, it does not exist. Okay, and that was part B that we saw. All right, so here's another picture of where that happens. So on part A, it's saying find the limit as x approaches 1, and it has a little negative, which means from the left. So if you kind of trace the graph from the left, as the x value gets closer and closer to 1, f of x is getting closer and closer to negative 2. But if I approach this same x value from the right-hand side, okay, then the y value is getting closer and closer to 1. All right, so because the left-sided limit and the right-sided limit are not the same, this limit, okay, the limit as x approaches 1 does not exist. All right, so what we're going to do here is we're going to graph some functions, and we're going to talk about their left and right-sided limits and then see if it's continuous, okay? So first off, on this graph, I'm not going to spend a whole lot of time about how to come up with this, but if you divide a number by itself, you're going to get 1. All right, and so what this is going to do is I'm putting an open circle here because it's going to cause us to divide by 0. We know that's not a point. And for numbers like 1, 2, 3, 4, 5, you divide a number by itself, you get 1. Now for the negative numbers, this is going to be a negative 1 because the top is going to be positive, the bottom is going to be negative. But again, we don't have a point at 0. Okay, so that's what that graph looks like. All right, so the left-sided limit, all right, as x approaches 0 from the left, all right, that is negative 1. But the right-sided limit, as x approaches 0 from the right, that's positive 1. Therefore, this limit does not exist. All right, and that's going to cause this to not be continuous. It's not continuous for 2 reasons, okay? And it's not continuous at x equals 0. It is continuous everywhere else. All right, this is because f of 0 is not defined, or you could say undefined, and the other reason, if that wasn't good enough, the limit as x approaches 0 does not exist. Okay, so let's look at another example. Here we have a piecewise function. Again, I'm not going to spend a lot of time on how do you graph piecewise functions. Okay, this is x squared. This is the parent function parabola, but we're starting up here at 2. So we need to really start at the point 2, 4, and it's just going to be a curve up like that. All right, 2x minus 1. We know this is going to be down here, up 2 over 1, up 2 over 1. And it looks, I'm just short of connecting. Looks like that. So I already know this is not going to be continuous. All right, just based off of my previous definition of continuity. What about the left-sided limit? As x approaches 2 from the left, the y is getting closer and closer to 3. And one thing that you could do here is you could actually plug 2 in. All right. 2 times 2 is 4, minus 1 is 3. All right, part B, the right-sided limit, 2 squared is 4, or you could look at it on the picture. And we already said we knew this wasn't continuous. We need to write where it's not continuous. It's not continuous at x equals 2, and we've got to give a reason now, an algebraic reason. All right, and this is because the limit as x approaches 2 does not exist. All right, so moving on to the next piecewise function. I'm going to draw a quick graph again. All right, here I have x minus 1. So it leaves a little open circle here with a down 1 over 1. And then 3x minus 1. Oh, I'm going to fill that circle in, and this one has a slope of 3. It's going to be steeper. And so there's what our function pretty much looks like. We have a limit from the left as x approaches 0 from the left. That's going to be a -1. The right-sided limit, same thing. This tells me that it should be continuous, and it is continuous. It's continuous because f of -1 is defined. The limit from the left equals the limit from the right, meaning that it does have a limit, and the limit is that point. Okay, and it makes sense that it's continuous. All right, so this is using the table on your calculator for numbers 4 and 6 only. The rest meaning use common sense, use algebra. We're going to find these limits again, the left-sided limit and the right-sided limit, talk about the limit existing and whether it's continuous. All right, so it says we need to use the calculator on number 4. So let's pull up the calculator. Let's type in so this looks like the numerator is x minus 2. The denominator is x squared minus square root of x minus 2. Be pretty hard to work with this algebraically. We're looking for around c equals 2. So what I'm going to do is do what we kind of did in the other lesson. I'm going to make the table start at 2, but I'm going to make my change in my table be really small so I can see what this limit is. All right, so if I kind of move up, I can see that as x approaches 2 from the left, which is when you want to look at first, these numbers are basically 0. So the left-sided limit is 0. What about the right-sided limit? Also 0. Remember, this is scientific notation, so these are equal numbers. Okay, so let's mark our answers down. We said the left-sided limit was 0, the right-sided limit was 0. That means that the limit does exist and that it is 0. It is this number. If it's the same, if these two numbers are different, then the limit would not exist. All right, so is this enough to prove continuity? Well, in this case, it is enough because the limit exists. It equals what f of 2 would be. So, in other words, if f of 2 is 0, then this all works out quite nicely. And we can see here clearly that it would. 2 minus 2 would be 0. And if I put in a 2, I'd get 4 minus square root of 2 minus 2, which would not give me a 0 in the denominator. It would give me some other number, and that's all I really care about. So yes, we do have continuity. All right, so let's move on to the next one. Now, I didn't say I had to use my calculator here, so this implies that we should be able to do this without the calculator. Now, we could graph this again, or we could just think about it logically. If I plug in a -1, the left-sided limit is going to come from the less than or equal to side, and the right-sided limit is going to come from the other piece. This is a piecewise function. So let's plug in a -1 in for right here. 3 times -1, that's -3, plus 7, that's 4. That's the left-sided limit. Now, f of -1 actually belongs to this, but if we're just looking at the right-sided limit, we could plug -1 into the right side piece. So -1 squared, that would be +1, plus 2, that would give you 3. Now, since these two numbers are different, then the limit does not exist. And if the limit does not exist, you really don't even need to think too much about the continuity. Okay? This says if it's not continuous, we need to write why. It's not continuous because the limit as x approaches -1 does not exist. All right, let's look at number 6. And number 6 was, again, one that they said you can use the calculator for. So let's plug that in. And the reason we don't really know how to work with this algebraically is because of that absolute value in the denominator. So remember that you can get absolute value by doing math, number, ABS. You can also find that in the catalog. If you've ever forgotten where anything is, you can look up anything you want in the catalog. Okay, so we have it typed in. We want to go to our table, and we want to set our table to start at the C value that they give us, which is -5. And we want to look at this left-sided and right-sided limit. Okay, so I can see here -5, I have an error, all right, and this may or may not be an issue, but I can see that 1.6 is the left-sided limit, that -1.6 is the right-sided limit. So let's record our answers. 1.6 left-sided limit, -1.6 was the right-sided limit. Since these two numbers are different, then we do not have a limit existing, and that makes part D easy. This means that this is also not continuous. All right, and the reason it's not continuous is because the limit as x approaches -5 does not exist. That limit has to exist, and it has to be at the point f of -5. If either one of those things don't happen, the limit doesn't exist. Okay, so number 7 is another one we can actually do without the calculator. If I factor this numerator, and we've seen this algebraic trick, all right, what ends up happening is I can cancel, and that makes sense. At 1, you know, this top part's the function everywhere except for where x equals 1. So I can cancel that out, and it really shouldn't make an issue. So really the top part is just an x plus 1, and there's a hole at 1, and that hole is taken up by the second piece of this piecewise function. All right, so if there's only one part where I use the second piece, then that makes the left-sided and right-sided limits easy to find. I should just be able to plug in f of 1. All right, 1 plus 1 is 2. So from the left and from the right, my limit is equal to 2. And this makes part C easy, since these are the two the same. Yes, that limit exists, and the limit is 2. All right, now, just because I'm answering yes to part C doesn't mean yes to part D. Remember, the limit has to exist, but it has to equal the point at that number. All right, now remember, f of 3 equals, or I'm sorry, not f of 3, f of 1. What does f of 1 equal? 3. Remember, that's where we go to that second part. There's a hole in the first part, but there is a point in the second part. So these two numbers do not match up. We have a limit and we have a point, and they're not the same value. Okay, so no, this is not continuous. The reason it's not continuous is the limit as x approaches 1, I'm sorry, -1, let's say of f of x does not equal f of -1. Oh, I'm sorry, I was right before. There's no negative there. There we go. Okay, so let's look at this next really strange picture, and there's actually a lot of things that I could be asking you, and I'm just going to ask you just these few things, and maybe we'll do a little bit more practice in class. So I'm looking for the right-sided limit of this function g of x. We'll just say everywhere you see curve, that's g of x. And so as x approaches -2 from the right, what is the y value approaching? It is approaching -3. That's what the y value is. Okay, over here we have -2 from the left. So as x approaches -2 from the left, the limit is 2. So we can see here that we have discontinuity at -2. We don't have a singular limit. And so let's just keep practicing. This limit does not exist. Record that. All right. Now, over here at 5, or I'm sorry, at 6, the right-sided limit of 6, it looks like +4. Okay, right up here at this point. There's a hole at 6. There's another point, but the right-sided limit is 4. Let's go ahead and skip down here. The left side limit of 6, as x approaches 6 from the left-hand side, that's at -4. So if I asked you for just the limit as x approaches 6, that would also be a does not exist. Okay, this looks like this is 2 from the left-hand side. So as x approaches 2 from the left-hand side, the y value is getting closer and closer to 3. All right, this is the right-handed limit of 4. So at 4, it's doing the same thing on both sides, and we can see that probably this is a vertical asymptote. The graph is just going up, 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 up. And you might be tempted to write infinity here, but if you remember from that first lesson of this chapter, these are finite limits. A limit as x is approaching a number, we would not write that it equals infinity. We would write that it does not exist. Okay? If x is approaching infinity, you could say that that limit is equal to infinity because that's an infinite limit. These limits, though, does not exist. All right, what about 0 from the right? Well, that's 0, and this is a situation where the left-sided limit would have been the same if I had asked you. Okay, and for the last question, this is a thinker. It says, for what value of the constant c is the function f continuous for all real numbers? Now remember, for continuity, we need f of 3 to be defined. Well, it would be. It would be defined by 3c plus 1, whatever c would be. Okay. We also need the limit to exist, and we need it to equal that point. Well, in order for this limit to exist, this needs to be connected. This needs to be where the left-sided limit equals the right-sided limit. So really what this boils down to is we need cx plus 1 to equal cx squared minus 1. And we need this to take place at x equals 3. We don't need it to take place anywhere else. So I can actually plug in 3 in for x. So this is going to be 3c plus 1, and this is going to be 3 squared. I'm going to go ahead and write that as 9, because remember, 3 here is the x. I'm going to write that as 9c minus 1. And just solving this out a little bit, you end up getting 6c is equal to 2. So c is equal to 1/3. So as long as c is equal to 1/3, then everything should work its way into place. We should have the left-sided limit be equal to the right-sided limit. Therefore, the limit would exist. It would equal f of 3. Everything should be continuous. Work out for continuous. All right, so bring your questions to class.